Okay, in this presentation we're going to look at confidence intervals for proportions. So it's a straightforward enough question. An insurance company experiences claims from 290 insurance policies in a year on a portfolio of 900 policies. So essentially we can see that we have a sample proportion there of 290 out of 900. I'll come to that actually shortly, but you always sort of look at these questions and sort of think, is this mean or proportion that we're asked to investigate? Sometimes you won't be told. Only one claim can be made on a policy in a year. Okay, that's just to sort of simplify matters essentially. That just sort of clarifies that it's a very simple case where there is 290 out of 900. The company assumes that all policies are independent of each other. Essentially what this is sort of setting up is that it is setting it up as a Bernoulli random variable or binomial experiment essentially. Okay, which is to say it's keeping it simple. Okay, determine a 95% confidence interval for the proportion of policies on which a claim is made in a year. Okay, so essentially what we're going to do is construct our confidence interval. Now the components of a confidence interval are the point estimate, the quantile, and the standard error. Okay, so the point estimate, which I just touched on previously, is p hat, which is equal to 290 out of 900, and that gives us a value of, there we are, and that gives us a value of 0.322. Now the sample size is 900, which is a large sample. Okay, so we can assume normality by the central limit theorem. That is to say, we can use this expression here. Okay, p hat is normally distributed with a mean of p, the true population proportion, and this value here. This is the standard error essentially. Well, what we're going to do is estimate the standard error using our point estimate here. Okay, so p hat times 1 minus p hat over n. Okay, now because it's a large sample, we would get to assume the normal distribution. Okay, so essentially it's a 95% confidence interval. So essentially the quantile we're going to use is 1.96. And we would actually use 1.96 quite a lot, but every so often it's just good to back it up a bit where this 1.96 is coming from. So it is from the standard normal distribution, and it's the 97.5 quantile. Okay, so why it's 97.5, there is a good reason for that, but we'll come back to that another time. Okay, so 1.96. Essentially what we're going to do here is put everything together. This is our point estimate, this is our quantile, that's our standard error, and that's the general form of a confidence interval. Point estimate plus or minus quantile times standard error. Okay, so 0.322. Essentially what we have to do is just work it out now. Okay, so our estimate for the standard error, we will use our estimate of p hat for p there, just to work it out. Okay, 0.322 times 1 minus 0.322 over 900, work that out. So, and there we have the other two values there, 0.322 plus or minus 1.96. This bit here requires a bit of number crunching here essentially. This standard error is actually the tough bit for this question here. Okay, essentially what happens is when you start to work it down, multiply that out, you get 0.2183 divided by 900. You get a very large figure like that. Okay, or a lot of digits. Okay, now I have it there to 7 decimal places. So just because you have to account for all those zero terms, but when I get the square root of that expression there, that square root of the standard, or express the standard error as one single value, 0.01557, and essentially I have the two other numbers there. Okay, let's just sort of revert back to 4 decimal places after a while. I mean, through the question you might have to go to more decimal places, but let's probably finish up in 4 decimal places, my own personal preference. And 0.322 plus or minus 1.96 times 0.01557, that's 0.322 plus or minus 0.0305, and that will give us an upper bound and a lower bound and an upper bound of 0.92915 and 0.3525. Okay, again, the rounding error and when you do these calculations might give you values close to that or near that, but hopefully that is where we are at. Okay, we'll leave it there.